Good afternoon, Review Committee. My name is Sean Rickson, and presenting alongside me are Nathan Chow and Sean Bayabaro. Over the last semester, we've created a new way to manufacture acetaminophen. The pharmaceutical market is one of the largest industries in the world and continues to grow rapidly owing to increasing consumer health awareness, improving distribution channels, urbanizing lower middle income nations, and the lasting effects of the pandemics. Analgesics are a class of drugs within the pharmaceutical market that have seen the most significant increase in demand over the last 3 years. These drugs relieve pain and reduce inflammation, with both prescription and over-the-counter products available. Acetaminophen is not only one of the most demanded analgesics, but one of the most demanded over-the-counter drugs on the market. A familiar brand is shown as Tylenol. The global acetaminophen market was valued in 2021 at an estimated $9.4 billion US, and it's expected to reach nearly $15 billion US, growing at a staggering 7% CAGR. The upstream sector is primarily focused on the formulation of active pharmaceutical ingredients, or APIs, which is the drug component that produces the desired biological effect. The API acetaminophen is manufactured in powder form, with bulk demand composing around 80,000 metric tons globally. Within this market, manufacturing cost is a critical factor to success because consumer behavior is strongly dictated by price. As such, a clear economic opportunity is present to revolutionize acetaminophen manufacturing to be a cheaper and greener process. The production process is historically and presently performed as a batch process. However, continuous manufacturing is thought to present a multitude of potential benefits, spanning time and resource savings, flexibility, and control over reaction conditions, which include concentration, pressure, and temperature. It is proposed that a continuous process could be cheaper and more sustainable. Thus, this project designs both a batch process and continuous process to determine whether and under what conditions the purported benefits can be achieved. The batch and continuous plants are designed 30,000 metric tons per year of dry powder acetaminophen, targeting 30% of global demand. There are several routes for acetaminophen synthesis. Project authors recommended to focus on a process that begins with p-nitrophenol, which undergoes hydrogenation to p-aminophenol, to which acetic anhydride is added to yield the API. However, a thorough analysis of many synthetic pathways was conducted in an exercise to reduce cost and limit hazardous operation. These reasons support the decision to procure from p-aminophenol as opposed to manufacture the molecule and begin with the acetylation step. With this reaction pathway, the first step in the synthesis is to acetylate p-aminophenol. This is done with acetic anhydride in excess and water to convert the excess acetic anhydride to acetic acid. To optimize the ratio of reactants to achieve maximum yield, multiple coupled variables were evaluated and are presented on the succeeding slide. Their optimization led to the most economical overall mass and energy balances, which the values are shown here. After making acetaminophen, the solution is crystallized and filtered before being purified and then recrystallized and dried. The acetic acid solution as a byproduct is then distilled for resale. Now, acetaminophen crystallization presents numerous challenges as the small molecule is polymorphic with 5 variations. Form 1 and Form 2 are the only polymorphs that form under the operating conditions of this plant. However, consistent Form 2 growth has not been achieved on a bulk scale to elute a purity higher than 50%, whereas Form 1 can obtain purities greater than 99%. Thus, this project will build on established processes of obtaining high purity Form 1 crystals, and this is the market standard. To build the necessary balances, it was important to make a sound decision on which composition to use. Presented in the 5 fingers, one can see that solvent composition impacts solubility, nucleation orders, growth rates, and purity. Optimizing these 5 variables, it was found that the larger the solvent ratio, the most overall benefit. And an iterative analysis revealed that an 8:2 ratio would result in the most crystal yield, and from this, the kinetic data was obtained with this composition. Following the balances, to ensure all aspects of the process could be optimized, a series of hand-calculated numerical solutions were developed and linked. The numerical solutions made use of thermodynamic first principles to keep consistent reaction profiles and conditions between processes. As pricing became integrated into these sheets, minimization functions ensured the process operated as efficiently as possible. With those preceding calculations, presented here is the complete batch flow diagram. The plant's staggering of reactors is not shown, but the succeeding economic analysis accounts for having multiple of the same process units to optimize both time and cost. To develop the continuous plant, the following considerations were made. Many of the processes were kept identical, but the reactors now used a CSTR, continuous stirred reactor model, screw press filters, and a fluid bed dryer. Very conservative estimations were also used for their respective throughputs. Here, the continuous process is modeled one-to-one to the batch process. The true novelty in this project is not displayed on any singular reactor, rather the small changes made to each process that ensure purity and yield. It is important now to highlight the optimizations that were completed for both processes. For the batch, a batch time of 2 hours was optimal for reactor sizing. For the continuous, 2 CSTRs and crystallizers were selected to ensure reaction control and fluidity, even with the added capital cost. For heating and cooling agents, sodium chloride brine and calcium chloride brine were selected, where the slightly increased operating costs were favored to minimize capital costs. Understanding the full plant development, we can now present the true economic superiority of the continuous process. To elude some of the major cost differences, the continuous process does not require intermediary storage vessels, which total to $14.3 million in the batch process, and instead make use of cheap inline heat exchangers. Further, the batch reactor and filter costs total to $35.2 million compared to the $29.9 million of the continuous process. This 20% difference is attributed to more efficient heat transfer, leading to less equipment and smaller reactors in the continuous scheme. Further, the batch process is 82 process units compared to the 69 for the continuous process. Additionally, the continuous process also sees significant operation benefits. With fewer moving parts, the plant can run for a larger portion of the year and requires less maintenance. Additionally, the process sections require 2/3 the number of operators compared to batch. Combined, these benefits attribute to just over $2 million in annual cost savings. So, at a price of $4 a kilo, the continuous process will see a 15-year NPV of $38 million with an IRR of 33%, compared to the grim $7.3 million and 18% for batch. Sensitivity analyses demonstrate that the continuous remains a more profitable investment across all the respective tested variables. Fixed costs were used as a proxy to plant scale to reach an understanding of what production conditions may prefer batch to continuous. While the difference between batch and continuous IRR appeared to converge as plant scale reduced, it was found that even a 50% reduction in output showed continuous to be 10% more profitable. Additionally, if the economy of scale correlations used for the continuous process happen to be an underestimation of the actual cost, the continuous process can become 50% more expensive and still have an IRR 5% greater than batch. Recognizing the significant scale of this plant, India was the chosen location, and with Wharton healthcare professors, a plan to make partnership with NGOs to facilitate community development was developed. We also considered current good manufacturing processes with the design of the plant to ensure public safety with our product, and also ensure that we could receive approval from FDA for sale in the US. Lastly, given that we are producing powders, it was important to ensure that dust does not impact workers' health through the use of appropriate PPE, dust collectors, and dedusting booths. For further optimizations, there is possibility for further exploration of semi-continuous processes to further reduce costs by integrating patch and continuous process units. Lastly, to facilitate recalls, residence time distribution can ensure pseudo-batches, providing product protection. It is recommended that future analyses gain true understanding of activated carbon needs and composition. Pilot scale tests should be performed to understand the degree of variability to the theoretic model. Additionally, the pilot scale should include polymorph sensors and examine purity. In summary, not only does the continuous process result in lower equipment costs, but it requires less maintenance and fewer operators. The continuous process also offers more control over the temperature and reaction profile. Finally, there is a greater ability to be flexible to demand fluctuations. Overall, the positive social and environmental impact justifies further exploration of continuous manufacturing processes in the pharmaceutical industry. All of this has the hope of lowering the price of generic drugs for all.